Welcome back. So we're going to continue looking at rate of change, and we're going to throw in some y-intercepts, and it's all within a real world context. So yes, lots of word problems. I know, your favorite. So Aunt Maggie's car broke down on Interstate 10. Braden's towing charges $57 hookup fee and $2 per mile towed, while Patrick's towing charges a $45 hookup fee and $2.50 per mile. So it wants us to sketch the graph that represents the charges for Braden and Patrick's towing. So if I start with Braden, okay, so Braden charges a $57 hookup fee and $2 per mile towed. Okay. All right, so Braden charges what are we talking about? T for total. So T equals, so the total is made up of the $57 hookup fee plus $2 per mile. And then Patrick is a $45 hookup fee and $2.50 per mile. So T equals, so a $45 hookup fee plus $2.50 per mile. And if you wanted to put the zero, you absolutely can. So I've just set up two simple little quick equations, and now I'm going to graph them. So our input is the amount of miles because the total depends on, well, how many miles are they towing the vehicle? So mileage goes on the x-axis, where total charge is going to go on the y-axis. Okay, so it's probably not super often that we're only going to get towed 1 mile. I mean, maybe, but so maybe do like 5, 10, 15, 20, 25 miles. That seems like a lot. So the total charge. Well, let's see. We're starting at 57 and 45. So let's just put a break in the graph. And let's see, if we're going at 5 miles, so if I plug that in, 2 times 5 is 10. So 67, so we're jumping from 57 to 67 to 77, 87, if we keep that pattern going. Okay, so we'll get up to around 100. So here, $2.50 a mile, so for 5 miles gives me increases of $12.50, so 45. Okay, so to 100 should be good. All right, so I'm going to start at, I guess, 40. And I'll just since we're going up by 10 and $12.50, I'll just number by tens. So 40, 50, 60, 80, 100, 120. I'm thinking that should get us started. Okay, so again, Braden is starting at, okay, so I'll make Braden blue. So Braden's starting at 57, so about there. So at 5 miles, I'm going to add another, so 67, 77, 87. Do you guys get what I'm doing? Because I just did 2 times 5. So for every 5 miles, we're going to increase by $10. So I'm just jumping. So 97, 100, 107. All right, that's plenty. So then Patrick only starts at 45, but is growing at $12.50. So that's going to go up to, so 5, so $52.50. And then 65, 77, 50. So 90. And then 102, 50. So gaining. So Patrick is definitely starting to gain on Braden. So Patrick looks, at first, Patrick is definitely going to be cheaper, but once we go past a certain number, Patrick is going to exceed Braden's cost. So it all depends on how many miles are you going, which company are you going to want to use. So both situations, it says, which of the following statements are true regarding this situation? Okay, so both situations can be modeled using linear functions. Yes, I'm increasing by 10 each time I have 5 miles and 1250 every time I have 5 miles. So that's a constant rate of change. So yes, both can be modeled using linear functions. All right, so the y-intercept of the function that models Braden towing charge is 2. So the y-intercept for Braden, so over my y-axis, that's definitely not 2. Nope, it's actually 57. Well, technically 0.57. If, we should be precise. So the rate of change of the function that models Patrick's towing is 2.5. Well, let's see. Patrick's towing, rate of change, 2.5. Yes, that's absolutely true. And the y-intercept of the functions that model both situations represent the hookup fee. So the y-intercepts, that's where we're starting, whether we, even before they even drive us anywhere, just for showing up and hooking up the car, we have to pay. So the y-intercepts, yes, those are the hookup fee. Check. And the rate of change of the functions that model both situations represents the miles traveled per hour. Okay. There's one little thing that messes that up, because M is for miles, yes. Miles traveled per hour? No, that's definitely not. It just represents the miles traveled. So if it just said miles traveled, that would be true. But they put in that per hour? Yeah, no, that's not right. So these are both linear models. Our hookup fee, so when you have an initial amount or initial fee that you're charged, that's going to be your y-intercept. And then from that y-intercept, we're adding on depending on what our rate of change is. So that just shows how much we either increase or decrease at a constant rate. So let's look at, let's say we don't have a real world problem and we're just given an equation. So it wants us to consider the following equation. So we're going to compare slope-intercept form versus standard form. So slope-intercept form, these might sound familiar. Slope-intercept form is y equals mx plus b. Okay? Whereas standard form is ax plus by equals c. So notice, y is isolated in slope-intercept form. Standard form, ax plus by equals c. You just have your variables on one side and your constant on the other. Standard form is very helpful for very little. Slope-intercept form, we will use a lot. Before we move on, I want to dive a little bit deeper into slope-intercept form, okay? Because it really has so many useful pieces. All right, so slope-intercept form. M is our slope. So again, what's that phrase that we use for slope? Rise over run. Okay, that's going to come in real handy when we're graphing. Now, B is a good starting point, all right? That is our y-intercept. So if B is positive, that means we have a positive y-intercept. If B is negative, we have a negative y-intercept. okay? So I have got some steps over here. You can either pause this, but we're going to keep coming back to these anytime that we want to graph, okay? So let's go ahead and look at equation A. So equation A, 4x minus 2y equals -6. All right, so that is in standard form. Standard form is not useful for graphing, but slope-intercept form surely is. So I've got 4x minus 2y equals -6. Okay, this is where that solving comes into play. So the better you are at solving, the easier time you'll have with this. So I want slope-intercept form, so notice y is isolated. So I'm going to go ahead and isolate my y. So I'm going to move over my 4x first, so it's positive. So I'm going to take a -4x from both sides. So -2y equals, now notice mx plus b, so I'm going to write the mx term first. So I'm going to write -4x first, and then follow it by -6. It wouldn't be incorrect if you switch those. I'm just trying to write it in a way to where I end up in the proper format, so I don't have to rearrange stuff at the end. Okay, so -2y, or -2 times y, so I'm going to divide by -2. So I need to divide all of my terms by -2. So y equals, so -4 divided by -2, that goes in evenly, so I end up with a positive 2x, and then -6 divided by -2 plus 3. So when we go to graph this, let's come over here and look. When graphing using slope-intercept form, first, plot the y-intercept. So let's give ourselves a place to start. So our y-intercept, +3. So I'm going to start at +3. And from +3, I'm going to use my slope. Now, slope is rise over run. Well, I see a rise, but I have no run. So what can I put this over that won't change the quantity? Well, I can divide anything by 1. It doesn't change it, so 2 over 1. So from your y-intercept, use the slope. Rise over run, sorry. And we'll try and get 3 to 4 points so we have something nice to connect. So my rise over run is +2 over 1. +2 over 1. No. That was wrong. I ran 2 instead of up. So, oh no. So I ran out of room on my graph. So since I can't rise 2 and run 1 anymore, I'm going to come back to that point. I'm going to do the exact opposite so that I stay in the line. So now I'm going to go down 2 and left 1. Notice I'm still in line. I just want a couple more points, down 2, left 1. And now we can connect our points. Now I have something that's shaping up to be a line. So I'm going to connect. Beautiful. Okay, so I would recommend that you go ahead and pause the video and try and do 3x plus 2y equals 6. Try and do that yourself. Okay? And then when you're ready, come back and check your answer. Alrighty, so I'm going to go ahead and put this in slope-intercept form. So I'm going to isolate my 2y. So first thing, subtract 3x. So I have 2y equals, I'm going to write my mx first, so -3x plus 6. And I'm going to divide all of my terms by 2. So y equals -3/2 x, or you can write -3x over 2, remember that same thing, and then plus 3. All right, so let's try it out. Again, where do we begin? I have a y-intercept of +3. Hey, that's what we had last time. All right, so apparently our graphs are going to overlap. So from here, I am going to use my slope. So our slope, -3. So from this point, I go down 3 and then +2. So right 2. Down 3, right 2. Okay, and I'm going to have one over here. So I'm going to come back and I'm going to do the exact opposite, up 3 and left 2. So I've got plenty of points, so I'm going to connect. So come up here. And beautiful. So even though I color-coded my lines, if you're ever putting more than one line, well, really more than one graph at all, on the same coordinate plane, you technically should always label them. So this is y equals -3/2 x plus 3. And this one is y equals 2x plus 3. So, I mean, technically, if you're color coding and I know what you're talking about, I'm okay. But again, if we want to keep our math correct, that's really how you should demonstrate it. One last piece. It says, which of the following statements is true about our graph? Okay. The slopes of both lines are the same and the y-intercepts are different. Well, if the slopes were same, then they would both be going in the same direction. But I see that I have a negative slope because this line is decreasing. This one is a positive slope, so that's definitely not true. The slopes of both lines are different. Well, that's true. We just talked about that. Slopes are different. Yep. And the y-intercepts are the same. Well, where's our y-intercept? Go to that y-axis. Yeah, that's correct. I guess we can stop. You can keep looking if you want, but we're good. So I hope that makes sense. This is why solving equations is so important right here. So please make sure, don't make any simple little arithmetic errors here, because most of you will get the graphing down super quick, but make sure when you're putting it in slope-intercept form, you don't accidentally drop a negative or something like that. All right, so go ahead, try those out, have fun. I'll talk to you soon.